Hello friends, I Professor Darshan from Terna Engineering College Dharashiv welcomes you on my YouTube channel for this subject head Control System Engineering. So friends, as far as our today's session is concerned, so we will try to learn the basic process in order to plot the dynamic characteristics of that control system, right? So basically we will try to learn this terminology whose name is nothing but what, as you can see, the root locus. So we will try to learn how to plot this root locus curve for a given control system, right? So let us quickly go through the objective. As you can see, our objective is to what? We are supposed to plot the root locus curve for this given closed loop unity gain feedback system whose open loop transfer function is nothing but what, which is mentioned in this numerical. The open loop transfer function denoted by this g of s equals to k upon s into s plus 2 plus 2j times of s plus 2 minus of 2j, right? So first of all we need to understand there are 7 or 8 different basic design steps through which we can plot the dynamic characteristics of that control system. The name given to the dynamic characteristics of this control system is nothing but what? The root locus curve, right? So one by one we will try to discuss all these design steps. Okay friends, so in that first step, what we need to do in that first step, here I will write, we are supposed to determine the number of loci which we need to plot within that root locus curve. So number of loci equals to what? Maximum number of either poles or zeros. So we need to understand how to determine these two desired frequencies of that given control system. Their names are nothing but what? The poles and zero. So whenever the denominator polynomial is being equated to 0, at that time we will able to determine the desirable frequency whose name is nothing but what? Pole. And when the numerator polynomial is being equated to 0, at that time we will come to know how many number of zeros we are having in that given open loop transfer function of that unity gain feedback system. So as a result of doing this, first of all we need to determine how many poles and zeros we are having with us. So carefully if we try to observe the numerator polynomial, so within that numerator polynomial we don't have any term belongs to that s, means we are coming out to this conclusion ki number of zeros equals to 0, means we don't have any 0 here, right? Now as far as the poles are concerned, so as I told you earlier, there are 3 identical terms within that denominator polynomial which are being equated to 0. So first one is nothing but what? S. So s equals to 0, right? When the second term within that denominator polynomial is being equated to 0, so we will come to know s equals to minus 2 minus 2j, right? This will be s1, and s2 will be what? When that third term is being equated to 0, so it will become minus 2 plus 2j, right? So we are having 3 different poles, right? Out of that 3 pole, one is real and 2 are the imaginary pole. First pole is being equated or is being located at origin, right? So accordingly, how many number of loci we need to include within that root locus plot? Maximum number of poles or zeros. So we need to include, as we don't have any zeros, the number of poles equals to 3. So maximum number of poles equals to number of loci. So ultimately number of loci equals to 3. Then within that second step we need to plot the pole zero plot, right? So this root locus is always plotted within this S domain representation, which consists of this real and imaginary part, which ranges from minus infinity to plus infinity plus j omega to minus j omega, right? Now as we know, we don't have any zeros and we are having 3 poles. Out of that 3 poles, first pole is being located at 0. If suppose this will be minus 1, minus 2, minus 3, and towards the minus infinity, plus 1j, this will be 2j, this will be 3j, like this, 1j, minus 1j, minus 2j, and this will be minus 3j, right? So our first pole is present at origin denoted with this cross sign. Second s1 equals to what? Minus 2 minus 2j and minus 2 plus 2j, right? So this is minus 2 and minus 2j, right? Similarly, this will be minus 2 and plus 2j, right? So this will be S2 and this will be S1, or we do undoubtedly we do can change its order. This will be S1, this will be S2, this will be S2 and S1. Order doesn't matter. What is important for we people to understand where these poles are being located. So obviously S1 is located within that second quadrant because its real part is nothing but what? Minus 2. Its imaginary part is nothing but what? Minus plus 2j. So it will become minus 2 plus 2j. And the second complex pole is present within that third quadrant, whose real part is minus 2, imaginary part is nothing but what? Again it is minus 2. So minus 2 minus 2j located within that third quadrant, minus 2 plus 2j located within that second quadrant. So this will be step number 3. Then after that, within that step number 3, right, we need to find out the real axis loci here. Real axis loci means the starting and ending point of our root locus, which we need to determine, right? So for that purpose, what we need to do, consider the first pole as a reference pole which is located at origin, and what we need to do, if the number of or the summation of poles and zeros which are present to right hand side of this reference pole equals to an odd number, then definitely we do can say that the root locus will exist within that certain interval, right? So this is the predetermined logic which is being used to determine real axis loci. In order to determine this real axis loci, consider the first pole as a reference pole, and we need to count how many number of poles and zeros we are having to the right hand side of this existing pole. So as you can see, we don't have any poles and zero towards its right hand side. So obviously we do can say that this root locus is not present from this 0 to plus infinity. Another important characteristics of this root locus is nothing but what? Root locus is always symmetric within this real axis. Never it is being plotted within that imaginary axis, that we need to understand. Then after that, the second pole which is present at this point, that is nothing but what? Minus 2 plus 2j and minus 2 minus 2j. Apart from this, one by default pole we used to have which is present at that dead end of this real axis towards this negative axis. Means what? At this minus of infinity, always we are having one pole which is present at minus of infinity, right? And when we count, this pole is being considered as a reference pole. So ultimately towards its right hand side, how many number of poles we are having? Always we are having 3 different poles. One is located at origin, another 2 poles which are being located at quadrant number 2 and quadrant number 3, right? So this root locus is present in between minus infinity to 0, right? So real axis loci, in this way this real axis loci have to be determined, right? What we need to do, once that particular poles or 0 can be considered as a reference pole, so we need to count how many number of poles and zeros we are having towards its right hand side, right? If the number of poles and zeros which are being present to its right hand side is equals to odd number, so definitely that pole can be considered as a real axis loci, right? Then step number 4 which we need to understand. Okay, let us continue towards the design step number 4. Within that design step number 4, we need to determine the number of asymptotes and angle of asymptotes. So basically asymptotes or asymptote is nothing but what? A straight line or tangent which is approaching towards the infinite value, which is to be plotted within this frequency domain representation of dynamic characteristics of that control system. Is that is nothing but what? Root locus. So first of all we need to understand how to determine how many number of asymptotes which we need to show within this root locus plot or within that root locus curve. So number of asymptotes is always equals to number of poles minus number of zeros. So as we are having 3 poles and we don't have any zero, so how many asymptotes we need to show? We need to show the 3 different asymptotes. Then once the number of asymptotes is being tabulated, after that we need to determine their relevant angles, right? So angle of asymptotes is being given by this expression 2x plus 1 upon 3 into 180 degree, right? Where this unknown variable x that can be iterated for n number of times starting from 0, 1, 2, 3, 4 up to n. That depends upon how many number of asymptotes we are having with us. Here how many asymptotes we are having? Here we are having 3 asymptotes. So this x that can be varied from 0 to 2, 0, 1, 2. So accordingly a1 asymptote angle number 1 equals to what? 2x plus 1 upon 3 into 180 degree. Now x equals to 0, so asymptote angle number 1 equals to 60 degree. Asymptote angle number 2, so 2x plus 1 upon 3 into 180 degree. X equals to 1, so it will become 3, 2 plus 1, 3, 3 will get cancelled, so 180 degree. Similarly, asymptote angle number 3, 2x plus 1 divided by 3 into 180 degree, where x equals to 2, so 2 into 2, 4, 2 to the 4 plus 1 divided by 3, so 5 by 3 into 180 degree, right? So 3 6 is 18, so 60 into 5, 5 6 are 30, 300, right? So asymptote angle number 1 equals to 60 degree, asymptote angle number 2 equals to 180 degree, and asymptote angle number 3 equals to 180 degree, right? Here I will write A1 equals to 60 degree, A2 equals to 180 degree, and A3 equals to 300 degree. So in this way asymptotes and their angles are being tabulated within this design step number 4. Then after that design step number 5 that we need to understand, right? So step by step we will try to learn. So within this step number 5, right, we need to determine the centroid of asymptotes denoted by sigma c, which exactly equals to summation of real part of pole minus summation of real part of 0 divided by p minus of z, means number of poles equal minus number of zeros. So centroid basically the intersection point on this real axis belongs to each and every loci, right? Or we can say that the intersection of this real axis loci which is present on that root locus plot, so denoted by this sigma c. For that purpose we need to collect the real part belongs to each and every pole as well as each and every zero. So as we don't have any zero, we are having 3 poles. Out of that 3 pole, one pole is located at origin, and as far as the remaining 2 poles are concerned, so their real part is nothing but what? The pole number 1 minus 2 plus 2j and minus 2 minus 2j, so their real parts are nothing but what? Minus 2. Again it will get added with this minus 2 divided by p minus z, which exactly equals to 3, so 4 by 3, so 3 1s are 3, 1.33 something minus, right? So this will be the intersection on that real axis in order to plot the angle of asymptotes, which are exactly equals to 60 degree, 180 degree and 300 degree. So here I will write sigma c equals to minus 1.33, which is to be tabulated from design step number 5, right? Then design step number 6 is nothing but what? The intersection of these asymptotes on that real axis, means breakaway point, right? Okay friends, so once the number of asymptotes, number of loci along with angle of asymptote, centroid, pole zero plot, all these first 4 or 5 steps are being completed, then after that we need to come across to the 2 important steps, step number 6 and step number 7. That will be the last 2 steps in order to plot this root locus curve for this unity gain feedback system, whose open loop transfer function is nothing but what? K upon s into s plus 2j into s plus 2 minus of 2j. So whenever we are having such type of imaginary pole, at that time one more additive step we need to include within this root locus plot as compared to the real pole, right? So we do can have the real pole and we do can have the imaginary pole. So whenever we are encountering with such type of imaginary pole, at that time we need to determine the angle made by this pole with respect to 0 on that real axis. The name given to this angle is nothing but what? The angle of departure, denoted by phi d. So here phi d equals to what? 180 degree minus summation of angles belongs to poles plus summation of angles belongs to all 0. So here we need to understand as we don't have any s term which is located within that numerator polynomial, means we don't have any zeros, and as far as the poles are concerned, so one more time such type of s domain representation is to be drawn, in which the first pole is located at origin, second pole is located at minus 2 plus 2j, and third pole is located at minus 2 minus of 2j, right? So here what we need to do, we need to determine this angle of departure. First of all, we need to determine the angle made by this pole with respect to 0. So we are having 3 poles. Out of that 3 pole, first pole is being located at 0, then second pole is located at minus 2 plus 2j, right? So what we need to do, here that pole is being located, so first of all we need to interconnect this pole with respect to 0 which is located on that origin, right? And this particular angle, right, that particular angle which was made by this pole located at which location, minus 2 plus 2j, with respect to this 0 which is present on that real axis, can be called as a phi p1. Are you getting my point? Phi p1 is nothing but what? The desired angle made by this pole with respect to this 0 which is located on that real axis, right? Now as these two values are same, this is also minus 2 and this is nothing but what? This is minus 2 and this is nothing but what? Plus 2. Apart from this sign, these are one has the same value, what we can say. So similarly, the total angle for this quadrant is how much? 90 degrees. So half of this, that much is how much? 45 degrees. So 45 degree plus this angle is nothing but what? 90 degrees. So 90 plus 45. So which exactly equals to 135 degree. So 135 is nothing but what? Which we can say that phi p1 equals to 135 degree. Up to this point, the angle is how much? 90 degree. Apart from this 90 degree, this resultant line is to be drawn within the center of this second quadrant. So obviously, remaining angle will be at 45. So 90 degree plus 45 degree, obviously, which exactly equals to how much? 135 degree. Now the question arises, in same manner we need to, or with the help of that protector also, if you put the protector like this here, right, then also you will come to know that this angle with respect to this real axis is nothing but what? 135 degree. Then the second pole is present at minus 2 and minus 2j. So one more time, see what we need to do, the angle made by this pole with respect to this real axis, which exactly equals to how much? Definitely we do can say that if we extend this line like this parallel to this reference real axis, so angle made by this pole with respect to this real axis is exactly equals to 90 degree. That can be called as a phi p2. So phi p equals to what? Phi p equals to phi p1 plus phi p2 equals to phi p, and phi z equals to what? Phi z equals to 0, because we don't have any 0, because as we don't have any s term which is being located at that numerator polynomial. So angle of departure for this pole which is being located at which location? Minus 2 plus 2j. So angle of departure for pole number 1 is exactly equals to 180 degree, right, minus this 135 plus 90 degree, right? So obviously which exactly equals to how much? Minus 45 degree. So minus 45 degree is nothing but what? The angle of departure for pole number 1, right? Now let us quickly go through this fact. This pole and pole number 1 and pole number 2, these two poles are apart from each other by an amount of 90 degree, due to which if the angle of departure for this pole is exactly equals to minus 45 degrees, so obviously the angle of departure for pole number 2, which is being present at -2 minus 2j equals what? Plus 45 degree. So this will be the step number 6, in which we need to determine the angle of departure for each and every pole which are being located within that denominator polynomial, right? Then after that, what we need to do now, it's time to plot the root locus curve. So before plotting this root locus curve, now finally what we need to do, we need to determine the intersection on imaginary axis. I will write here. Intersection on imaginary axis. This will be the last step which involves in this root locus plot. So for that purpose, the relation is like this: d plus k n equals to 0. Now the question arises what this d stands for. So denominator polynomial plus this unknown variable k times of numerator polynomial equals to 0. So that will be the characteristics equation, right? Okay friends, so within this step number 7, which will try to tell us the intersection points of this root locus curve on this imaginary axis, right? So in order to determine the intersection point on that imaginary axis, this is the relevant statement which we need to use as far as this root locus plot is concerned. That is nothing but what? D plus kn equals to 0, where d and n, these two are the denominator and the numerator polynomial which are being mentioned within this numerical itself. So this denominator, as it is, we need to write here s into s plus 2 plus 2j into s plus 2 minus of 2j plus k into n equals to 0. Then after that, simply we need to multiply these two parentheses with each other, right? So as a result of multiplication, it will become s square plus 2s minus 2js plus 2s plus 4 minus 4j plus 2js plus 4j plus 4, right? Remaining terms are nothing but what? Plus k, and numerator polynomial equals to what here? We don't have any s term which is present within this numerator, so equals to 1. So after that, what we need to do, see this minus 2js plus 2js will get cancelled. This minus 4j plus 4j will also get cancelled. So the remaining term is nothing but what? S square. This 2s plus 2s, 4s, this 4 and this 4 equals to 8 plus k equals to 0. So again one more time, when this s is being multiplied within this parenthesis, s raised to 3 plus 4s square plus 8s plus k, right? So this will be the characteristics equation for that given unity gain feedback system, whose open loop transfer function is nothing but so and so, right? Then in order to determine its intersection on that imaginary axis, we need to declare the coefficients of this Routh array according to Routh's stability criteria. So for that purpose, we need to map this characteristics equation like this will be A0, A1, A2 and A3. Then after that, we need to declare the such type of Routh array here, right? In which the highest degree of freeze is how much? 3. So 3, 2, 1 and 0. So as far as first row is concerned, we need to collect all the elements which are lying at even position. As far as row number 2 is concerned, we need to collect all the elements which are lying at odd position. So accordingly, it will become 1804 k, and also it will become 0. Then what about these terms which are being located within this third row? So in order to get this term, what we need to do, this 4 times of 8, 4 8s are 32 minus k upon 4. This term will also become 0. Now as far as this last term is concerned, so how it is being tabulated with the help of its previous two rows. Previous two row elements are nothing but what? 4k, this 32 minus k upon 4 and 0, right? So this 32 minus k upon 4 into k, right, divided by this whole term again. So these two terms will get cancelled. Remaining term is nothing but what? K, right? So from this we can determine the marginal value of this k, right? So marginal value of this k is nothing but what? As you can see, as far as this element is concerned, 32 minus k upon 4, here I will write 32 minus k upon 4, it should be greater than 0. So obviously k, it should be less than 32. So the marginal value of k is how much here? 32, right? But what we need to do by taking into account the intersection on that imaginary axis, this step is being considered. So in order to determine the intersection of that imaginary axis, what we need to do by using the auxiliary equation method, we can determine the intersection point on that imaginary axis, right? Now auxiliary equation means what we need to do. Auxiliary equation means first of all we need to observe which row is providing the marginal or the maximum value of that k. So here this step number 3 is responsible to provide the marginal value of that k, which was exactly equals to how much? 32. So its previous row is being considered. So its previous row coefficients are nothing but what? S raised to 2. So the auxiliary equation will become what here? 4 times of s square plus k, right? Somewhere which is written on that board here. See, the auxiliary equation equals to what? 4s square plus k equals to 0, because the coefficient of 4 is how much? S raised to 2 is a even number. So the lowest even number apart from these two is nothing but what? 0. So it will become 4s square plus k equals to 0. So as we know, the marginal value of k is how much? Already it has been tabulated, 32, right? So accordingly 4s square equals to minus of k. By doing certain mathematical simplification, we will come to know s square equals to minus of 8, right? When this 8 is being placed within this square root sign, right? So the negative value which is present within that square root sign will try to give the imaginary value started with this j. So the square root of this minus 8 is nothing but what? Plus minus j 2.82. So this is nothing but what? The intersection point on that imaginary axis. So far, in order to plot the root locus curve, what we need to do? We need to follow all these 8 steps, right? And finally we will try to plot the root locus curve. First step is nothing but what? Number of loci. Second step is nothing but what? Full zero plot. Third step is nothing but real axis loci. Fourth step is nothing but what? The angle of asymptotes and number of asymptotes. Then after that, we need to determine this fellow that can be called as a centroid. Once that centroid is being calculated, after that we need to determine, as we are having the imaginary pole, angle of departure. After this angle of departure, intersection on that imaginary axis. And finally, now we will plot the root locus curve for this given control system. Okay, so finally we will try to plot the root locus curve for this given unity gain feedback system, whose open loop transfer function is nothing but which is mentioned in that numerical, right? So before plotting this root locus, let us try to collect all the parameters which we had tabulated from design step number 1 to the design step number 7. So these parameters are nothing but what? We are having 3 asymptotes and their angles are nothing but what? 60 degree, 180 degree and 300 degree. So with respect to this centroid, these angles are to be shown. So centroid is nothing but what? Minus 1.33. After that, we have tabulated the angle of departure for pole number 2 and pole number 3. Obviously, first pole is present at this origin. The pole number 2 is nothing but what? Minus 2 plus 2j, which is shown on this S domain representation. This will be the pole number 2, minus 2 plus 2j. The angle of departure for this pole is nothing but what? Already it is being tabulated, minus 45 degree. And as I told you earlier, these two poles are quite symmetric apart from 90 degree to with respect to each other. So angle of departure for this pole which is present within the third quadrant will be opposite of that, plus 45 degree. And after that, the intersection on this imaginary axis, these two intersection points are nothing but what? Plus minus 2.82j like this, right? So see, this will be the real axis, this will be the imaginary axis, right? Now according to this particular numerical, the starting point of this root locus is origin and the end where it being terminated towards the minus infinity. So the root locus is present in between minus infinity towards the 0, right? Then after that, what we need to do? First of all, we need to show the angle of asymptotes, right, with respect to centroid. So centroid is exactly equals to minus 1.33. So how this plot is being sketched within that graph paper only. So the intersects are nothing but what? Ranges from minus infinity to plus infinity and plus j omega to minus j omega. So sigma c is minus 1.33. So this will be minus 1, minus 2. So in between these 2 points, somewhere it is being located sigma c, right? So first angle of asymptote is 60 degrees. So with the help of this protector, see, this will be the 60 degree line, asymptote number 1, right? Then after that the asymptote number 2 is how much? 180 degrees. So obviously when we put this protector like this, right? So this will give you the asymptote number 2 line. With this dotted line we need to show. This will be A2, whose angle is exactly equals to 180 degree. And finally asymptote number 3, whose angle is nothing but what? 300 degree. So here it will come like this dotted line. This will be A3. This angle is exactly equals to 300 degree. This angle is exactly equals to 180 degree, and this angle is nothing but what? 60 degree. Then after that this is how these poles are being located within that second and third quadrant. Now it's time to plot the angle of departure. The angle of departure for this pole number 2 is exactly equals to how much? Minus 45 degrees. So what we need to do? We need to put this protector like this, and we need to measure, this will be the 45 degree line like this, right? So the angle of departure is how much here? 45 degree here, minus 45 degree, right? And it will try to intersect this imaginary axis, because this root locus is always parallel to this asymptote line. Intersection point is how much? Plus 2.8, right? And similarly for that pole which is present within that third quadrant, the angle of departure is how much? The angle of departure is 45 degrees. So what we need to do? We need to put this protector like this. So obviously this will be the plus 45 degree like this, and it will try to intersect, it will try to intersect this imaginary axis on 2.8 something like this, right? Here also the intersection point is how much? It will be up to this point, this is 2j, and up to this point 3j. So below this 3j, the intersection point is how much? Plus and minus 2.82j, right? So this is how your root locus will look like, which is always symmetric within that real axis. We are having 3 poles. One is present at 0. These are the 2 remaining poles. Their angle of departures are nothing but what? Minus 45 degree. So minus 45 degree like this, and this root locus will try to intersect this imaginary axis on which point? Plus 2.8, plus 2.8, and minus 2.8. So below this plus 3, somewhere it will try to intersect. Similarly, this root locus will intersect this negative axis on minus 2.8j. So this is how your root locus will look like. So I just hope you had understand all these things belongs to this root locus curve. Thank you.